So looking at page 90, we start getting into one of the more important characteristics of Taylor and Maclaurin series, specifically the Maclaurin. We can manipulate these special series by using the following techniques. We can substitute into the series, we can multiply or divide by a constant and or a variable, add or subtract two series, differentiate or integrate, and recognize it as a sum of a geometric power series. That's a little bit more involved, but we'll get to it. All right, so for the first example, it says find a Maclaurin series for the sine of x squared. All right, so what we can do is go back and snag our sine of x. All right, so copy, paste. And while I'm at it, I see in the second one, I'm going to need a cosine. So let me grab that. I'll write in the typed stuff in a sec. And then for the last one, we need exponential e. So I'm just going back in time to page 88 and 89 and snagging that information. All right, so focusing on the first one, we know that we're dealing with the sine of x being equal to this expansion for the interval of negative infinity to infinity. All right, so all that's telling me to do is if I want f of x is equal to sine x squared, everywhere I have an x in my Maclaurin series for sine, I'm going to replace it with an x squared. All right, so it says find the first four non-zero terms. So we only have three indicated here, but we can figure out the fourth one pretty easily just by following the progression. So instead of an x, it's an x squared. Minus 1 over 3 factorial x squared to the third, so x to the sixth. All right. Plus 1 over 5 factorial x squared to the fifth is going to be x to the 10th. Plus, I'm sorry, the next one would be minus because it's alternating. So 1 over, we did 1 over 1 factorial, 3, 5, so the next one would be 1 over 7 factorial. Now it's just a question of x to the what? Well, the powers of the sine Maclaurin is 1, 3, 5. Next one would be 7. So x squared to the 7th would be 14th. But by following the pattern, you see the exponents increasing by 4 every step of the way, so you can rely on that piece of information as well. All right, there is an arithmetic nature to the exponent. All right, so we can just kind of hold on to that. All right, now if we go for the nth term, it's really just a matter of replacing, because everything else remained the same. So I'm going to snag this. But I'm going to replace the x with an x squared. Everything else remained the same except for that. Now that could be cleaned up because the power to a power, let me just make this pink, and multiply the two powers. And so I'd be looking at a series expansion that when put into summation form, we'd start off with n equals, well, that begs the question, does n still equal 0? So let's hold off on that for a sec. So we'll say n equals, we know we're going to infinity, negative 1 to the nth. The alternating nature didn't change. All right, so negative 1 to the nth is fine. X to the 4n plus 2 over, now did our factorials change? Our factorials remain the same. So 2n plus 1 factorial. So what I would want to do here is investigate, or at least just determine whether or not an n equals 0 still makes sense for the lower bound. All right, so if I plug in a 0 for n up top, I get a positive for the negative 1 to the nth. If I plug in a 0, I get x squared, which is what I want. If I plug in a 0 on the bottom, I get 1 factorial, which is also what I want. All right, so it is okay to keep calling this 0, and there we have it. All right. So really, it is just a matter of expanding it out and observing the relationship, but you also kind of get from this that it's okay also to just pop it right into the quote-unquote formula, the summation formula. All right. So the second one is cosine of x true for negative infinity to infinity. So if I follow the expansion by multiplying cosine, so f of x is x cosine of x, I get x minus 1 over 2 factorial x cubed plus 1 over 4 factorial x to the 5th minus 1 over 6 factorial x to the 7th. They said first 4 non-zero terms, so we're good there. We don't have to go any further. All right, but we look at what's happening here. Everything is remaining the same except for the power. So plus 0, 0, 0, 0, 0, dot, 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 dot. So this part is going to be the same. But now the relationship here is that if you can look at it a couple of different ways. You're multiplying this by x, which is the same as multiplying it by x to the first, which means keep the base at the exponent. You'd be looking at 2 to the x, or 2 to the n plus 1 is what I meant to say. All right, so that's one way to look at it. Another way to look at it would be to say, well, my exponent here in every case is 1 more than whatever the number is in front of the factorial symbol. All right, so just take the expression that you use to generate the number in front of the factorial symbol and add a 1 to it, and you now have your exponent. All right, either way would be okay, or at least conceptually. All right, and so that's going to be equal to the sum from n equals, again, we leave that blank until we get a reason to believe that it's still going to be 0. We knew that nothing changed here. These values remain the same, so I'm not worried about that. It's really just this. I want to make sure that if I plug a 0 in for n, that I'm going to get the appropriate exponent, and I do. If I plug in a 0 for n, I get a 1, so it's okay to call this a 0. Two things would have to happen, or two things could happen. If it didn't, 1, you'd adjust your exponent, figuring that you probably made a mistake, or 2, you'd adjust the lower bound for the summation, figuring that there was a reason why you needed to do that. All right. The last one, e to the x plus e to the negative x over 2. All right. So I'm going to work off of this, but I need an e to the negative x. All right. So before jumping right into my h of x, what I'm going to do is I'm going to write this as e to the negative x, or I'm going to write an e to the negative x, replacing every x with a negative x. All right. Even powers are going to remain the same. Now this whole thing, I snagged it from a previous page, but this whole thing amounted to a 1. So they're really, I mean, this is just to demonstrate how it equaled a 1. That's going to stay as a 1. All right. And even if you put a negative x in for x, you raise it to the 0th power, it's still going to a 1. The odd powers, on the other hand, negative x to the first power becomes a negative x. So this becomes minus x, because 1 over 1 factorial is 1, plus 1 over 2 factorial. Negative x squared is x squared. Negative x cubed is negative x cubed. So this becomes negative 1 over 3 factorial x cubed. So now what we see here is that there really is no difference in the absolute value of each term of the expansion. The only thing that's changing is that it's now alternating. All right, so what I'll do here, so plus dot 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 plus 1 over n factorial remains the same. The x to the nth even remains the same. I just have to tack on a -1 raised to the whatever power makes sense. Now, since our summation is going to start off with a 0, -1 to the 0th starts us off with a positive value in the expansion. So that works out nicely, so I'll just put an n there. All right. So this is going to clean up to the sum from n equals 0 to infinity of, I'll combine the numerators. This will be -1, oh, I cannot write without zooming in, -1 to the nth, all right, over n factorial times x to the nth. All right, and still it's going to be true for the same interval, all right, because if it's true for -infinity to infinity for e to the x, it'll be true for -infinity to infinity for, oh, I don't need a double underline there, e to the negative x. You just think about the e to the x versus e to the negative x function. It's everywhere continuous, everywhere it exists, everywhere differentiable, everywhere. All right, so now what I want to do is take my h of x, which is going to be e to the x plus e to the negative x over 2. All right, so it's the average of the two expressions, e to the x and e to the negative x. So it's a question really of, do you want to average, just going back here, you can add or subtract two series, or multiply or divide the series by a constant and or a variable. All right, so do I want to add or subtract each term, or add and subtract each term, and then divide by 2, depending on, you know, what we're asked to do. In this case is addition, but there could very well be a situation where you have to subtract, so keep that in mind. Or do we want to just work off of the summation form of it, or both? I say both. All right, so what I'm going to do is I'm going to take each term, so 1 plus 1 is 2, divided by 2 is equal to 1. So I'm going to start essentially creating the series expansion here by averaging each term together. So 1 plus 1 is 2, divided by 2 is back to a 1. All right. Now this again is just a complicated way of saying x, a positive x, x plus x, x plus negative x is 0. So that's going away. So I'm not worried about that one. All right. 1 over 2 factorial, that's the same as 1/2. A half plus a half is a whole. All right, so we're looking at 1x squared, but then divided by 2 is going to be 1/2 x squared. All right, basically the odd ones are going to cancel out. All right, so then it begs the question, okay, the next one, which would be 1 over 4 factorial x to the 4th, all right, that's going to be 2 over factorial x to the 4th divided by 2 is going to go back to 1 over 4 factorial x to the 4th. All right, so we're basically just combining our numerators, because the denominators serve, since they're common, they serve as a means for us to combine our fractions. All right, so that part's not bad. All right, so continuing the progression here, so plus, oh, we need 4. So yeah, it will still be a plus. So 1 is really 1 over 0 factorial x to the 0th, 1 over 2 factorial x to the 2nd, 1 over 4. So next is 1 over 6 factorial x to the 6th. So now we have the means by which we can come up with our general rule, which is going to be, well, we got a 1. We have an even exponent, and we have an even denominator as a factorial. So 1 over 2n factorial x to the 2n. All right. So replace n with 0. it checks out. Replace n with a 1, it checks out. Replace n with a 2, 1 over 4 factorial x to the 4th, it checks out. All right, so this amounts to the sum from n equals 0 to infinity of this whole shibbity bangity boomity 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 boom. All right, so I think personally a little bit easier to see how this combines together when you go term by term than it is to try to take these two and put them together. But it's still doable. It's just you have to take it case by case, because if you look at it and say, okay, well, in some instances -1 is going to remain a -1, and in some instances -1 is going to become a +1. When it becomes a -1, that's irrelevant. When it becomes a +1, that is relevant. What happens there? You get your relationship, and you go on your merry way. But coming up with the 2n is a little trickier. So page 91, it says find a Taylor series for each of the following functions by finding derivatives and using the Taylor formula. All right, so we know the Taylor formula at this point. We also know some general processes associated with the Maclaurin series that kind of help pave the way to understanding this stuff a little bit in a more reasonable fashion. Specifically, the idea that if it's centered around a value that helps make your exponential, in this case exponential, but your function more convenient for evaluation, then you're in good shape. So f of x we know is e to the x plus 3 minus 3, written right there in front of me. F prime of x is going to be another e to the x minus 3. So that tells me that all derivatives are going to be e to the x minus 3. So f of 3 is 1. All derivatives at 3 will also be equal to 1. All right, so that's a good situation when we want to expand using the Taylor series. We're going to say f of x equals e to the x minus 3. We're looking at 1. I don't know what happened there. 1 plus, it's 1 every step of the way. So 1 over 0 factorial x minus 3 to the 0th power. 1 over 1 factorial, which is 1. X minus 3 to the 1st. Plus 1 over 2 factorial x minus 3 to the 2nd. Plus 1 over 3 factorial x minus 3 to the 3rd. All right, and what we get from this is the idea, very importantly, that the numerator is going to be 1 in the instances in which all derivatives are equal to 1. All right, so this is really just an instance where we took a Maclaurin series and we made a substitutions composite function. We replaced the function, the x value of the function, with an x minus 3, but more specifically, or more generally, I guess, we replaced it with a function whose derivative is equal to 1. All right? It had no bearing via the chain rule on anything. All right? So we're looking at 1, that's not equals, plus dot, 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 1 over n factorial x minus 3 to the nth. All right, so this is going to be my summation. N equals 0 to infinity, and it's really just this expression. All right, but when it's centered around 0, it changes things a little bit, but really only a little bit, because if you think about it, you know, I'll kind of carry you through the derivative process. It's only going to be impactful in the sense that your f of whatever is going to be different. All right, so the derivative of e to the x minus 3 is still e to the x minus 3. When I center it around 0, it doesn't give you a 1 anymore. It gives you an e to the negative 3. All right, so you just think about what would happen here. It's going to change all our numerators, but it's not going to change anything else. All right, so if I want to use this approximation technique, expand it to give me a Taylor series, let me just make this look a little nicer. To get my g of x, all I'm going to do is replace every one with an e to the negative 3rd. All right, so all those coefficients of 1 now become e to the negative 3rd. The only thing is that there's no apparent coefficient here, so I have to just chuck it in. But every step of the way beyond that, it's more obvious. And so my general rule is just going to be whatever it was before multiplied by my new derivative. All right, so instead of my derivative being a 1, I'm going to multiply through by e to the negative 3rd. All right, and so the follow-up question is something I've already addressed. We could have used the Maclaurin series here, because one of our properties tells us that we can substitute into, I wanted the highlighter, substitute into the series. All right, so it's like, what are you substituting into the series? Oh, let me grab my Maclaurin. I'm substituting in x minus 3. The only trouble you'll ever run into here is based on the value that it's centered around. All right, so if I'm centered around 0, which makes it Maclaurin, then I'm going to get a derivative other than 1. If I'm centered around something that makes my derivative equal to 1, then I'm in better shape. All right, so e to the x minus 3 would serve to replace every one of these x's with an x minus 3. So I'd be looking at 1 over 0 factorial x minus 3 to the 0th plus 1 over 1 factorial x minus 3 to the 1st plus 1 over 2 factorial, and so on. All right, but when I'm dealing with, again, that numerator is the result of finding the derivative at a particular location. All right, so f of 0 for e to the x is equal to 1. F prime of 0 is also e to the 1. I'm sorry, e to the 0th, which is 1. I think I said e to the 0, e to the 1 a minute ago. I meant to say just a 1. All right, but f prime of 0 here is e to the negative 3rd. So that adjustment needs to occur, and so all of these 1s become e to the negative 3rd power. All right, so if you can make that relation or make that recognition, then you're in good shape. If I can transform all of these 1s to e's, that would be even nicer, but not the case. So the answer is yes. It would just take a little doing and a couple of mental steps. All right. So find a Taylor series, again, centered at 0. All right, so we'll keep that in mind. All right, so and you don't need, it says you don't need to find the general term. And again, it's going to have the same follow-up of could you have done this all using Maclaurin? And that's an ongoing thing. We'll keep looking at that. All right, but sine of x plus 6 pi over 6, I should say, because that's the correct way of saying it, has a derivative of cosine x plus pi over 6, has a derivative of negative sine of x plus pi over 6, has a next derivative as negative cosine x plus pi over 6, and then the fourth derivative gets us back to sine. All right, so now this is saying centered at 0. So pi over 6 is going to have a sine of 1/2. Cosine of pi over 6, radical 3 over 2. Negative sine pi over 6, negative 1/2. Negative rad 3 over 2. And then back to 1/2. All right, and so when we expand this out, we're saying f of x is the same as, again, the sine of x plus pi over 6, which in turn is going to, so we need our 1/2 plus, all right, so we have this issue here where it's not just a clean alternation of signs. It's a matter of, it's what does the trig function dictate. All right, in the case of 0, where sine of x is centered around 0, it was fluctuating between positives and negatives because all the cosine values disappeared. Here, all the cosine values are not disappearing, so we don't have that clean alternation between the 1/2 and the negative 1/2. We have some cosines along the way. All right, so we would say plus rad 3 over 2 over 1 factorial, so x. Now it's centered at 0, so I could just say just an x instead of parentheses x minus 0 to the first power. So then the next one would be minus 1/2. That's 0, 1. So now we're up to 2 factorial x squared. Yep. Then minus rad 3 over 2 over 3 factorial. That's going to be x cubed. And then they said to only go 4 terms, the first 4 non-zero terms. So we could stop there, because after that we start cycling back upon ourselves in terms of the coefficients. We're still going to increase in terms of the factorials and the powers, but that's where it's said to kind of leave things be. All right. Now, if we center it at negative pi over 6, all right, so our derivatives are going to remain the same. It's now g, so let me just make that quick edit. So sine of 0, so this is all negative pi over 6. But it's going to make the argument of the trig function equal to 0. So that's going to cycle us back to what we actually already know about a Maclaurin, when the sine function of x is centered around 0. It's going to amount to the same thing, because this is just a translated form, but we're also translating the center with us. All right, so sine of 0 is 0, cosine of 0 is 1, sine of 0 again is 0. Doesn't matter whether it's positive or negative. Then we'll have a -1 and then back to 0. All right, so we have that alternating relationship. So g of x being equal to, again, sine of x plus pi over 6 is going to be equal to, so now our coefficients are a lot nicer, so 0 over 0 factorial. All right, so 0 over 1, so the first term is gone, plus 1 over 1 factorial. Now it's centered around x equals negative pi over 6, so x plus pi over 6 to the first power. Then we're at the power, the second derivative is going to go to 0, so that's our 2 factorial, so we're up to 3 factorial, so minus 1 over 3 factorial x plus pi over 6 to the third power, so that's only 2 terms, we need 4, but we have a pattern emerging here, so plus 1 over 5 factorial x plus pi over 6 to the fifth minus 1 over 7 factorial x plus pi over 6 to the seventh dot dot dot. All right, so we have 3 terms, a little bit more complicated looking, but definitely a little bit more user-friendly in terms of the derivative part of it. All right, and if we needed to come up with a rule for this, it's going to be a little bit easier than the previous case. So, could you have found the either of these answers by substituting into the Maclaurin series for the sine of x? And the answer is, yeah. Right? Because the first one is centered around 0, so let me go grab a sine function somewhere. I think I have one. Oh, yeah, right here. All right, so for A, the only thing we would have to do, if you just compare what we have here to what we're ultimately dealing with, is we do have a substitution that needs to be made. All right, so we'd have to account for that. And then from there, we would have to account for the derivative. So, I mean, could we do it? It's not going to be pleasant, but it's definitely doable. All right. But the thing is, it's one of those things, like I would say probably you kind of only recognize that after you've done it. All right. So I would say here, to get from the sine of x to the sine of x plus pi over 6 just by substituting an x plus pi over 6, well, that's going to make it pretty ugly here. I would say it won't be easy. But there would be some adjustments that you could make to the Maclaurin that would get you eventually here. All right, but for the second one, different story. All right, because if you take a look at what we have on paper, quote unquote on paper, for B, and compare it with the Maclaurin series, you see it's identical except for the substitution. All right, so if you take a look at that and then just do a substitution of sine, that's not a marker, of x plus pi over 6, you could see that it's a perfect fit. It's just a matter of replacing every term with an x plus pi over 6. All right, so this would be, if I could just cut to the chase, the sum from n equals 0 to infinity. We have our alternating series, -1 to the nth. Instead of x plus pi over 6 to the 2n plus 1 over 2n plus 1 factorial. All right, so this one would be a yes, definitely. The other one would be Well, it's a little messier. I'm sure we could get there, but it won't be easy. All right, what's the difference? The difference is, in the case of A, yeah, it's centered around 0, but 0 is not convenient for the sine function. As in, we want to be thinking about what value of x would get us to the array of derivatives that we would get for the Maclaurin series. All right, so 0 doesn't do it, but pi over 6, negative pi over 6 does. All right, so if my derivatives, my array of derivatives for the sine function are 0, 1, 0, negative 1, 0, I would want to be thinking, no matter how complicated the expression is inside the sine function, is there a value that I could plug in for x in order to make that work out? All right, so what does that mean? It means, the old calculus rule of thumb, take whatever's inside the function, set it equal to 0, and solve. All right, for a sine function, that works out nicely. All right, we're really just looking for that first term. All right, because I want a 0 inside the sine function for that first term. All right, same thing with the cosine. For exponential e, I want the exponent to be equal to 0. All right, so x minus 3 centered around 3, x minus 3 centered around a 0. Yeah, we got there, but it wasn't as easy of a trip. We had to make, some adjustments.